Let's talk more about derivatives. So here, the first definition I have here, it's the one you probably have seen very often. It's the derivative of the function f of x at x naught. So x naught is a point in an interior point of an interval. So we're defining the first derivative as the limit definition. So that is right here. And if this limit exists, then we said that the derivative exists at x naught. So suppose I have a function that looks like that, and x naught happens to be this interior point right here. Let's call that x naught. So we will say that there exists derivative at x naught if this limit exists. Now what if we have a function that looks maybe something like this? Can we talk about derivative at this point? Let's call that point A. Well, because it's an endpoint, we can talk about one-sided derivative. For instance, we can approach this point from the right side, so coming from the right. So we can say, okay, let's rewrite it in this way. So we're approaching the limit as h approaches 0 from the right of f of a plus h minus f of a all over h. So that's what we call a right-hand derivative at the point A. Since there's no graph on the left side, we can only approach from the right side. Another one could be maybe looking at this point right here. Let's call that point B. And because that's also an endpoint, we can only approach from one direction. Let's say I can come from this side, approaching that number. So we can talk about the limit as x approaches 0 from the left. And this will also have one-sided derivative. So at the endpoint, we can talk about one-sided derivative, but when it's an interior point, we can just simply assume that the left side and the right side are equal, then the derivative exists. So if these two happens to be finite and same, then we will say that the derivative exists at that point, x naught or a or b, whichever it is. Now let me illustrate this idea by using an example so that you understand how to work with this formula. So suppose we have a function, let's say f of x equals x squared, only on the interval x greater than or equal to 0. And we want to find the derivative, of this function at x not equal to 0 or x equals 0 if it exists. So you might want to visualize this graph so that we know which sided derivative we're looking at. So let's suppose this is our xy plane, and x squared just on the right side, so pass through 0, 0, and then it creates this half of the parabola. So imagine this half doesn't exist. So we're looking at, will there be derivative at the point x naught equals 0? So this point right here. So because we can only approach from one direction, which is from the right, so we're approaching this way to 0, so we can talk about the derivative at 0 is a one-sided limit. So it's the limit as h approaches 0 from the right of f of 0 plus h minus f of 0 all over h. So I'm simply using this definition right here. And then using x squared, we're going to evaluate this limit. So we have the limit as h approaches 0 from the right, f of 0 plus h, well that's simply 0 plus h squared minus 0 squared all over h. And then I can simplify this a little further. I have the limit as h approaches 0 from the right, 0 plus h squared, that's just h squared, minus 0, that's just 0 over h. And we can cancel out one of the factor of h from top and bottom. We have the limit as h approaches 0 from the right of h. And then if I plug in 0, I get the limit to be 0. So therefore, we can say that this function has derivative at 0. and it's a one-sided derivative. Now let's take a look at this problem. So we're given the graph of f of x, and we want to show if f is differentiable at the point P. So that's right here. And we're going to do that by simply computing the one-sided limits. So we'll approach from the left and right. So we'll show that if the limit as h approaches 0 from the right of f of, let's say, a plus h minus f of a all over h, we'll see if that is equal to the limit as h approaches 0 from the left of f of a plus h minus f of a all over h. If these two-sided limits are equal, then it is differentiable at the point a, which is 0 in this case. So let's show. So this is what we want to show. So let's compute the right-hand limit. So the limit as h approaches 0 from the right, f of 0 plus h minus f of 0 all over h. So keep in mind that we're using a equals 0. So from the right side, we're going to approach this direction right here. So we're going to be using this function to evaluate this limit. So this is equal to the limit as h approaches 0 from the right. We're using the function x. So this will be 0 plus h minus 0 all over h. And this simplifies to the limit as h approaches 0 from the right, h over h. That is simply the limit as h approaches 0 from the right of 1. And we know limit of a constant is a constant. So this side we get 1. Now let's hope the left side we also get 1 to be differentiable at 0. Now we want to test the limit. So this was first. Now second, as h approaches 0 from the left of f of a plus h, well, we're using a to be 0. So let me go ahead and do that. 0 plus h minus f of 0 all over h. So from the left side, we're going to be coming this way. So we're using this function to evaluate the limit. So this is the limit as h approaches 0 from the left. So we're using x squared. That's 0 plus h squared minus 0 squared all over h. And simplifying this, we get the limit as h approaches 0 from the left, h squared over h. And one of the h will cancel out. We get the limit as h approaches 0 from the left of h. And then if I plug in 0 into this limit, I get 0. So you see how these two sides are not equal. So because the one-sided limit didn't equal to each other, therefore the function is not differentiable at the point P. So since these two limits didn't equal, we can say f is not differentiable at the point P, which is 0, 0.